Newton's law of universal gravitation. Gravitational force. Alright, so it has been well known since ancient times that Earth is a sphere and objects that are near the surface tend to fall down. Newton, if you remember from our dynamics, connected the idea that objects like apples fall towards the center of the Earth with the idea that the moon orbits around the Earth. It's also falling towards the center of the Earth. The moon just stays in circular motion since it has a velocity perpendicular to its acceleration. So if you think about circular motion, alright, acceleration is going to go towards the center of the circle, and velocity goes perpendicular. So the moon is going around in this circle, and it's just acting like we did in circular motion. Newton concluded that all objects attract one another with a gravitational force. The magnitude of the gravitational force decreases as the centers of the masses increases in distance. So if you think about it, the closer objects are to each other, then there's going to be more gravitational force. And the further they are from each other, there's going to be less gravitational force. Yeah. Alright, so if you remember, G equals 9.8. Well, now we have another constant, which is this capital G. And that is our gravitational constant. So in 1798, Henry Cavendish discovered big G using a torsion beam balance. He did not initially set out to measure G, he was instead trying to measure the density of the Earth. Mathematically, the magnitude of the gravitational force decreases with the inverse of the square of the distance between the centers and in proportion to the product of the masses. So, we've got this force, which is equal to this force, which you see here, and they equal big G times the mass of the first one times the mass of the second one divided by the distance between them squared. The direction of the force is along the line connecting the centers of the two masses. Each mass feels a force attraction towards the other mass along that line. So this one feels it towards the other one, and this one feels it towards the other one in the opposite direction. Newton's third law tells us that force on each mass is equal. So if you remember, Newton's third law was that there were equal and opposite forces. That means that if I drop a pen, the force of the Earth pulling the pen down is equal to the force of the pen pulling the Earth up. However, since the mass of the Earth is so much larger, that force causes the pen to accelerate down, while the movement of Earth up is completely unmeasurable. So since the pen is so much smaller, the movement of the Earth moving up is so tiny that you don't even notice it. What is the magnitude of the gravitational force between two 1 kilogram objects which are located 1 meter apart? So we've got our force of gravity equals big G times m1 times m2 over r squared. So then what we're going to have is the force equals, and you would plug in 6.67 times 10 to the negative 11. And you're going to multiply that. That's just going to be our multiplication. Times 1 times 1, because both of them are 1 kilogram, divided by 1 squared. So 1 times 1 is going to equal 1. 1 squared is going to equal 1. So when you multiply it times this, you're going to get this as your answer. What is the magnitude of the gravitational force acting on a 4 kilogram object, which is 1 meter from a 1 kilogram object? So we've got our force, gravity equals our big G, which we know is 6.67 times 10 to the negative 11, times M1, which was 4, times 1 for the second one, divided by 1 squared. So now we've got 6.67 times 10 to the negative 11 times our 4 times 1 is going to give us 4. And then divided by 1 squared, which is 1. We know that that is going to give us 4. So our final answer is going to be C. 2.7 times 10 to the negative 10. What is the gravitational force acting on a 1 kilogram object, which is 1 meter from a 4 kilogram object? So, if you recall, these are the same givens as the last problem. But now they want to know the force in the opposite direction, which is going to be the same. Remember, they are equal and opposite forces. So, our answer should come out to 2.7, the same thing. Number 4. What is the magnitude of the gravitational force acting on a 1 kilogram object, which is 2 meters from a 4 kilogram? So we're going to have our equation. But now our R is changing. So now we've got 6.67 times 10 to the negative 11 times 1 times 4 divided by 2 squared. So now 4 over 4 we know is going to equal 1. So 1 times the number is going to give us our 6.7. So we're going to just get that. Alright, what is the magnitude of the gravitational force between Earth and its moon? This is why it was very important that we did scientific notation, because we get the mass of the Earth over here, which is very big, so that's why it's in scientific notation, and the mass of the moon, which is also very big, and their distance is very big. So we would plug it in as 6.67, just like the last ones, 10 to the negative 11. But now our M1 is going to be 6 times 10 to the 24 times 7.3 times 10 to the 22nd and divide it by 3.8 times 10 to the 8th. And remember, that is squared because our radius is squared. What we're going to get in the end is C. What I would do is I would play around with your calculator. In class, I'm going to show you how to do it on our class calculators so that you can get this and multiply them and work it all out. Alright, so now the same thing is going to happen again, but now we are working with the radius and the sun. So make sure you write that equation out the right way, and you're going to get D. I want you to try all these out with your calculator and see if you get the right answers. So now gravitational field. While the force between two objects can always be computed by using the formula for force of gravitation, it's sometimes convenient to consider one mass as creating a gravitational field and the other mass responding to that field. So, basically what we did over here was they basically took M1 and they made it this capital M, the one that's in charge, and they made M2 this lowercase m. Okay? And now they got rid of that, and they got rid of this. So now they're left with little g equals big G divided by M over r squared. Get that gravitational field. The magnitude of the gravitational field created by an object varies from location to location in space. It depends on the distance from the object and the object's mass. Gravitational field G is a vector. Its direction is always towards the object creating the field. That's the direction of the force that a touched mass would experience if placed at that location. In fact, G is the acceleration that a mass would experience if placed at that location in space. Remember, little g for Earth is 9.8. So now this is just describing kind of what that G is. So which of these gravitational fields is the strongest? Well, you want to pick one that's got the closest distance, which would have the smallest r squared. So the closest would be here. Surface gravity. Now, planets, stars, moons all have a gravitational field, since they all have mass. That field is largest at the Earth's object surface, where the distance from the center of the object is the smallest, when r is the radius of the object. By the way, only the mass of the planet that's closer to the center of the planet than you contributes to its gravitational field. So the field actually gets smaller if you tunnel down below the surface. So basically what it's saying is if our r gives us the gravity, the closer you are and you're on the surface, that's going to be the most gravity. That's why we don't float off the Earth. We're there. Because our r squared is so much smaller, because now it's literally just the radius. Determine the surface gravity of Earth. Its mass is 6 times 10 to the 24th kilograms, and its radius is 6.4 times 10 to the 6th meters. So we've got our G equals Gm over r squared, which would be 6.67 times 10 to the negative 11 times 6 times 10 to the 24 divided by 6.4 times 10 to the 6th squared. And what you're going to get for your answer, and if you look, they just kind of typed out what I did. They got 9.7, which, when you round it, is close to 9.8, which is our G for Earth. Does it make sense now? Alright, so now they want to know on the moon. So, again, you're going to do the same thing. G equals big G over r squared, which is going to be 6.67 times 10 to the negative 11 times 7.4 times 10 to the 22nd divided by 1.7 times 10 to the 6th squared. It's all the same equation, you just have to plug everything in, and I'll show you how to do it on the calculator. And you get this answer. Again, we're going to do the same thing for this one, so I want you guys to try and set that up. Pause the video and try and set it up. Alright, so what you should have set up is this. And again, the Earth's sun is so much bigger than the Earth and all the other planets that's why its G is humongous. If you look, the sun gives this 272. Our 9.8 that the Earth has is like nothing. That's why the sun is able to keep all the other planets. And lastly, what we want to do here is compute G for the surface of a planet whose radius is double that of Earth and whose mass is triple that of Earth. So I want you to try that out. You can pause the video if you need to. Alright, and this is how to do it. So regardless, G is going to be in both cases. Okay, so you can cancel out that G on both of them. Alright, then we've got the 3 times the mass on Earth, so our M's kind of disappear and we're left with 3 there. And now on the bottom it's R squared, and we know it's 2 of the Earth, so 2 squared gives us 4. And then we know G on Earth, which is what's here, is going to be 9.8. So 3/4 of 9.8 is going to give us 7.32. So what I want you to do now is on Edmodo, I just want you to plug in what you did understand, what you didn't understand. And also, if you'll be using one of the class calculators, or if you're using one of your own, if you are using one of your own, I just want you to write what kind of calculator it is. So if it's like a TI-83, write that in. Thanks. See you tomorrow on, not tomorrow, on Wednesday.